Welcome to Mr. Hamilton's Math Bites. This video is about geometric sequences. I want to start off with a relatively simple example in this video. The first thing I want us to think about is a bank account. We've all had a bank account, we've all put some money in the bank account, and we've seen at the end of the month that we get a very small amount of money, typically only a few cents in our bank account depending on how much we have. Now, just suppose with me for a minute that we have $100 that we put in a bank account. Alright, that's what we're going to start with. And then every month, the bank is going to give us a 1% interest payment. Now that is exceptionally high. If you find a bank with a 1% interest payment, please tell me, because that's the best interest rate I think in the history of banks. But let's suppose, just for the simplicity of it, that that is the interest that they're paying you per month. That means after the first month you're going to have $101. All right, because what you've done is you've multiplied this by 1.01. Now I think something interesting happens now for the second month. Right, this is the end of the first month, this is the second month. In the second month, you now get $102.01. Well, why didn't they just add $1 again? Well, it's because they're multiplying the value they had in the previous month by another 1.01. And then the third month, again, we're going to have $103.03, again by multiplying that by 1.01. And then the fourth month, this is going to continue to grow. And you can see the picture that this is starting to form. We get 104.06. In the fifth month, we get 105.10. And in the sixth month, we get $106.15. Again, multiplying by 1.01 every single month. And what happens is this is something called compound interest. Compound interest. What that means is it continually grows every month. But the key about compound interest is that it's growing based on what was already there and the interest that was gained over the last however many months. All right, so it's based on the interest that was already there and the interest that it has accrued. Sometimes the word used. Now, that means that it's a good thing likely for us. We're gaining interest on interest, but we're only getting paid once a month. We're not getting paid every second or every day. So what we have here is we have a situation where we have to have a discrete case. It's an exponential growth, all right? It's going up, but it's not happening at every single time. Let's say this is $100 here, and so you're starting at $100 and you're going up little by little over time like this. And so you're seeing this exponential line form, but it's not a solid line. It only exists at those specific points, at those discrete cases. So let's keep that in mind as we move into the lesson. So we have three goals. Goal number one, we want to be able to determine if the sequence is arithmetic, which was the last lesson. We want to know if it's geometric or something else entirely. We want to be able to determine the general term recursive formula and any term value for a geometric sequence. We want to be able to solve applications of geometric sequences. That includes exponential growth and exponential decay, things that we should have seen and remember seeing from previously. Geometric sequences have a constant ratio. It's underlined there because that's super important. It's a constant ratio, sometimes referred to as a common difference factor. And so we look at an example to derive the formula, and you'll see how this comes about. 4, 12, 36, 108, 324. You might look at that and right away recognize, well, I'm just multiplying that by 3. This is times 3 again, and every time we're multiplying that value by 3, and you'd be correct. But can we get a formula that allows us to solve for any given geometric sequence? As soon as we have a constant ratio, whether it's a value we're multiplying by to get the next one, or it's a value that we're dividing by, or if it's positive or negative, those are all possibilities. But can we have an equation that allows us to solve that quickly, regardless of what the values are? And we can. So let's go ahead and do this. We want to derive a geometric sequence from 4, 12, 36, 108, 324. And so what I'm going to do first is I've got the term number listed on the left side here. Then I've got the term value listed here. All right, so the 4 is the first term, the second term is 12, etc. If we're to write that in terms of the initial value, this is just 4 times 0. The second one in terms of the initial value is 4 times 3. The next one, 4 times 9. The next one, 4 times 27. And then 4 times 81. As a multiple of 3, we could write that as 4 times, well, no multiple of 3. In the second case for 12, we could write that as 4 times 3, same thing as we had. But where things get a little different here is when we go to 36. This is 4 times 3 times 3. And in the case of 108, this is 4 times 3 times 3 times 3. You're going to get tired of saying 3's here in a moment. And in the case of 324, it's 4 times 3 times 3 times 3 times 3. In exponential form, makes our life a little bit easier. 4 times nothing is just 4 times, well, 4 times 1 is really what we have here. And 3 to the power of 0 is 1. So 4 times 1 is just 4. 4 times 3 is the same thing as 4 times 3 to the power of 1. 4 times 2 threes is 4 times 3 to the power of 2. Then we have 4 times 3 to the power of 3 and 4 times 3 to the power of 4. Now what you notice here, I hope, is as you continue on up here, what we're doing is we're starting with 4, and then we have a base of 3, and then this is to the power of the term number minus 1. The first term is to the power of 0. The second term is to the power of 1. The third term is to the power of 2, etc. So that's why the exponent is 1 behind the term number. That's what the n minus 1 means. Exponent is 1 behind term number. And as I pointed out earlier, if you graph this as far as term number versus term value, what you see is an exponential relationship, but an exponential relationship that only exists at discrete values, as I've highlighted here. Discrete values. Graphing the values of the sequences shows a discrete function. This is what it says in the box. The function Tn only exists at specific values. Notice that it is also an exponential growth relationship. It increases to the right. Since n is the term number, the value of the nth term is the last term in the sequence. And there's your t to the n equals 4, 3 to the power of n minus 1. The initial value is 4, and the common difference factor is 3. And so you might recognize some similarities here to what we saw in exponential growth when we studied that earlier in our course. And so see if you see that as we get to the general term. So in general, a is the initial value, and r is the common difference factor. So what we get in general is we get Tn equals a times r to the power of n minus 1. Tn equals a times r to the power of n minus 1. What we saw in the past when we looked at exponential growth was f of x equals a times b to the x. But the reason the exponent here is n minus 1 is because we always start at the first term, not at the 0th term. All right? That's the only difference. So sometimes you'll see instead of a Tn, you'll see an Fn, and that's just turning it into a function. In this case, n is a set of all real numbers, or sorry, a set of all natural numbers. That means 1, 2, 3, 4, etc. All the numbers you learned in kindergarten. The recursive formula, which I'm not going to derive for you here, but I hope is pretty obvious, comes from the fact that we start with the first term being a, the a value. That's defined as such. And then we say that Tn is equal to r times Tn minus 1. So that simply says that if r is the factor that we're multiplying each term by, then I take the previous term, I multiply it by that factor, and I get that new term. Then that new term becomes the last term, and I multiply that by the factor and get the new term again, and continue that over and over and over. So the recursive formula is not something that I can directly get to a term with. It's something that I have to use all the previous terms to get there. Let's see how this works with this example A. It asks us to state the general term in the recursive formula. We've already stated the general term. We know the general term is Tn equals a times r to the power of n minus 1. So this is just going to be 4 times 3 to the power of n minus 1. That's the general term. The general term. The recursive formula uses the fact that we're starting with T1 equals a. So that means in this case that the first term is going to be 4. And T2 then is equal to the r, the common difference factor, which is 3, times Tn minus 1, which is the 2 minus 1. So that really, you don't need to write that as such, but I just want to show you how that works. 2 minus 1 is T1. That simply says that T2 is equal to 3 times T1. And so T2 is equal to 3 times 4, which is 12. And we could say that T3 is equal to 3 times that number, T2, which is 36. That's not what it's asking us. It's not saying to come up with all the terms. It's asking us to state the recursive formula. So what I should say is down below T1 equals 4, I should say that Tn is equal to 3 times Tn minus 1, such that n is the set of all natural numbers, 1, 2, 3, but it can't be 1. It has to be greater than 1. Because if I have T1 equals 3 times T of n minus 1, then the n minus 1 would be 0, and I don't have a 0th term. These next examples will go a little bit quicker. State the general term recursive formula and T7 for the following sequence. Negative 243, 81, negative 27, positive 9, negative 3. The first thing I want to note is you may see that right away what the multiplication factor is. But I want you to first see that if we can't figure out what it is, we can always determine by dividing one term by the previous term. Always determine common difference factor by dividing it sequential terms by previous terms. So what that means in this case is we could say T2 divided by T1. Well, that's going to be positive 81 divided by negative 243. That gives me a value of negative a third. We could say T3 divided by T2. So one bigger divided by the previous term. And that's going to give me negative 27 over positive 81. That's negative 1/3. And check it with one more to make sure I'm on the right track. But I think it's pretty obvious that I am. I'm going to say 9 divided by negative 27. Well, that also is negative 1/3. Which that means is that R has to be equal to negative 1/3. If any of these was not negative a third, it would not be geometric. But we can see that multiplying again by negative a third gives me negative 3. So that means that the starting term or the initial term is negative 243. And the R value is negative a third. And so the general term that I can write here, the general term is Tn equals negative 243 because it's supposed to be in the term in A times R to the n minus 1. So it's negative 243 times negative a third to the n minus 1. Now n has to be the set of natural numbers here. There's my funny looking n. The recursive formula would be T1 equals negative 243. And then if you recall, it's Tn equals R times Tn minus 1. And the R value here is negative a third. So it's negative a third times Tn minus 1, where n is a set of all natural numbers such that n has to be greater than 1. And so if it's asking us now to find T7, well, I'm going to find it using the general term if I have it, because that's direct. And so I'm going to substitute 7 in for n. So my exponent becomes 6. Negative 243 times negative 1/3 of the exponent of 6. And that gives me negative 1/3.